So, like we said, we'll look at what our future energy needs will be. Okay, so we need to be able to model growth. So, in order to extrapolate energy use into the future, we need to understand how to model growth. All right, so here's a linear growth model. Okay, so what this is showing you is some quantity that is growing over time, and you would get a linear growth model, for instance, if it grows by the same amount. So let's do an example. Let's say your salary increases by $2,000 every year annually. So then your salary would increase linearly. Now, on the other hand, so this equation, what it's telling you, if your salary grows by a certain percentage every year, this is how it would grow, and then your salary would grow exponentially. Okay. So linear growth is when it happens by the same amount, and exponential growth is when it grows by a certain percent. So let's say if your salary grows by 3% each year, then it'll grow exponentially. Okay, so that's what these growth models are. So we'll linear and exponential growth. So for instance, you saw that when we were looking at energy use. Initially, when a new energy source comes online, it grows exponentially as we learn how to harness it more and more efficiently, and as the supply is present, is available. So so there again, this is linear growth, and this is exponential growth. Okay. Now, a useful piece of information in exponential growth is uh, the percentage by which it grows in unit time. dt is the unit time. So in this equation, time, you could be measuring the time in seconds, days, months, years, or whatever. And so that's the fraction that by what percentage did that grow in that time. Okay, so that's a useful piece of information. And here's something you can do. You can take whatever quantity it is that you're plotting, you can take the log of that uh, and um, plot it against time. So log of that quantity against time, and you'd get a linear quantity. So this should be log of that. So there's a typo here. And from the slope of this line, you can evaluate this uh, quantity A. The percent that quantity is growing in unit period. Okay, and that's useful for the following to calculate the following. We are interested in doubling time. Okay, so what that means is in what time period will the quantity double? So for instance, if your salary is growing annually by 5%, how many years before your salary doubles? That's the question. Okay, so the doubling time is natural log of 2 divided by A, the growth rate per period. Um, okay, so for a small growth rate, uh, the percentage is given um, in percent per unit time. The growth rate is given by this. This is the growth rate, and it's given in terms of the doubling time, like that. Okay, so that's just A in percentages. Okay, so here's the growth rate and doubling time. So let's say if you're let's use the example of your salary. So if your salary was growing by 3% per year, your salary would double in 23 years. Okay, so that's what this is saying. If your salary was increasing by 10% each year, your salary would double in 7.3 years. Okay, so that's the doubling time. Okay, and if this were the growth rate per year, so if you're okay, so that's what this table gives you. All right, so here's the world population for the past 1,000 years. So here we are roughly in 2000, year 2000, and this is year 1000, and this is population this is the population given in millions. So 7 7,000 millions would be 7 billion. So currently the world population is about 7.7 billion. Okay. So that's the world population. So here is the interesting number. Look at this. Back 1,000 years ago, the world population was this is a billion, so was about 250 million. Okay, that's less than the U.S. current U.S. population, and the population was steady for a long time, and it's been growing exponentially. Okay. Now, if the world population grew exponentially, kept growing exponentially, what would the world population be? So here are some scary numbers. What would the world population be in year 4,000, 2,000 years from now? Now, this really won't happen, but assuming an annual growth rate of 1.6%, which was, so the world's population grew exponentially at one point at the for uh, the 50 years between 1950 and 2000, it grew at the rate of 1.6%. That was an exponential growth. So if the world population kept growing like this, in 2012 it was 7 billion. In 190 years, it would be 142 billion people. And so, of course, that'll never happen. Okay? So that's what this table is showing you. And if it kept growing at that rate, in 2,000 years, it would be 45 trillion trillion. No, half a trillion trillion. That's what that number is. And so again, this will never happen. Okay. So the current world population is 7.7 billion. That's right now. And estimates of sustainable world population is about 100 billion, 10 billion. So a lot of scientists believe that the world population will stabilize at 10 billion and eventually start decreasing. Of course, the current world population growth rate won't grow for very long. And in fact, the growth rate has been declining. So here are some numbers. In the 50s, 60s, and 70s, the growth rate hovered around 1.6 and so on. And now you can see that it's almost at 1% growth rate. So, and if this trend continues, the growth rate will decline. Okay, keep declining. All right, so why are we talking about this? Well, we have a pretty good idea that the world will have about 10 billion people. That would be the world population. And so, what would be our energy needs? Okay. So now here are a couple of things that so our energy needs will increase with just the increase in number of people, and also as lifestyles increase per capita, the energy needs will increase. Okay, so you got a growing population, and as people get richer, you'll need more and more energy per person. Okay, so we'll need to bear that in mind as we search for more and more renewable energy solutions. Okay, so here's a graph that shows you that. So this is 2035, just 15 years from now, roughly. Okay. China has about 4 times the population of the United States, so these are projections. And so again, remember the US uses about 100 quads of energy. Okay, and so our energy needs will be steady, but while we have reached the peak of lifestyle, I mean, any more energy intensive lifestyle would really not be sustainable. so so ener- so this model predicts that China in 2035 will be using 200 quads. That's still per capita with 4 times the population. That's twice the energy. That's still half the energy intensity of per person in the U.S. Okay, so but still this is a problem. Okay, and hopefully all this extra energy will be coming from renewable sources, and we don't want it coming from, well, nobody wants it coming from fossil fuels. And so anyway, that's what this model is. And India also, which has a comparable population to China, will be using 1/4 the energy of China. Okay, so that's again 1/4, well, half of the U.S. So 1/8 of the U.S. Okay, so that's what this graph tells you. Okay, this graph just shows you OECD countries are mostly Western countries, and these are non-Western countries. Okay, so this is the energy use in quadrillion BTU. Okay, currently the world is using about 500 quads. Okay, so well, or almost 600 quads, and the world is projected to use about 800 quads by 2035. Yeah. uh, okay, so Mr. Hubert came up with a model, and it's held up quite well. So how does the how is an energy source utilized? So for Mr. Hubert says, initially as it's discovered and as you build up technology for utilization, the use of that energy source grows exponentially. And this is a model for a limited resource. It grows exponentially, and as supplies dwindle, uh, the amount of the resource starts declining. As you're reaching its depletion era, the prices go up, and then the prices go higher and higher, and you're running out of it, and the use of that resource goes down. So we saw that we saw this with the use of petroleum. So we are going back to the petroleum graph. So here we go. This is the use of petroleum, and many believe that we've reached the peak, or we passed the peak, and the use of petroleum will decline like that. Okay, so that's the Hubert model, and so many claim we have passed the peak for petroleum, and we are on the declining cycle. Anyway, so what's relevant is, so we had better put renewable sources in place quite fast, okay, for many reasons. This is the total use of resource. Okay, so when you run out of the resource, uh, the total use of resource uh, has maximized. So that's what this graph is. So we will stop now.